Welcome back to the OscopeWizard. Bedazzled hat. I had a whole explanation for it before. One of the junior OscopeWizards made this hat for me. I have snuck it out of her room without paying the $2. I probably owe her $2, but I just wanted to show it off because it seemed like such a cool Baby Friday piece. And I love it, and it is awesome, but it is a little bit heavy, so I'm going to take it off for just a moment while I talk. And I am going to go back to an apology from Tuesday. Hopefully everybody can still hear me. This is a constant problem on the show, whether you can hear me or not, but I think you can. Everybody says 2 thumbs up. So let's go back over the apology that I owe to you from Tuesday. So I was mansplaining about AC versus DC, and I said AC doesn't have the transmission line loss that DC has, which is a misconception that I fell right into, and I should not perpetuate misconceptions, and I apologize for that. So on that note, I wanted to go over, see if I can show it. Well, I think I could. Just do this. None. We will do no crop. Okay, on the screen, I said that AC voltage does not have the same loss as DC voltage on a transmission line, and that was incorrect. What is actually true is that power loss of a transmission line is inversely proportional to the level of voltage, so the voltage level. And on Tuesday, I was talking about 12 volts DC and 12 volts AC. That means that if the voltage levels are equal, the power loss is equal. Now, as the voltage level gets bigger, transmission power loss gets smaller. As the voltage level gets smaller, transmission power loss to the transmission line gets bigger. So the reason why it got in my head this incorrect assumption is that when we were setting out our power infrastructure 100 years ago, it was much easier for us to take a really high AC voltage level, and step it down to a voltage level that would work in our house. So the lines running around, the power lines running around might have 1,000 volts AC. In your house, it's 110 volts AC if you're in the US. It's 220 volts if you're across the pond. You're lucky guys, you get a little bit extra voltage. But to step down from 1,000 volts all the way down to 100 volts, a lot easier to do that using AC voltage. Now, modern technology would allow us to do it with DC voltage, but we've already set the infrastructure up. So to change everything, we would basically have to clear the infrastructure that we already made and start new. Now, sometimes there's a bad system that you need to clear out and fix, but our AC power system seems to be working just fine. So, incorrect. Sorry about that, guys. There is not magic with AC lines. It has much more to do with voltage level, 100% to do with voltage level. The website that I referenced is called bsharp.org. There's a physics article on transmission line loss, and I will link it in the description of this video so that you can read up on it on your own. So I've learned a lesson, stay in my lane. My lane is digital design, low voltages. That's where I operate and where I enjoy operating. So I will get back to the agenda for today. So what is the agenda for today? The agenda for today is building a DIY Sonos Style amplifier. I found a Raspberry Pi. Now we need to make it rumble so it has noise for my ear holes. Noise for my ear holes is what we're going for. The Raspberry Pi that we're using is a Raspberry Pi Zero. And on the last episode, I pointed out that the Raspberry Pi Zero does not have an analog audio output. So we are using a digital to analog chip. Let's see if we can find my digital to analog chip. Here's my digital to analog chip that I'm using. It is a PCM5102. I think it's a 5102 is the one that I'm using. It might be the 5101. Doesn't really make that much of a difference because this is the data sheet for all of them. And this digital to analog converter, what it does in life is let's see if I can put it on the screen here. It takes the signal from the Raspberry Pi, the digital signal, which is I2S, it's 3 lines. It takes that, converts it into analog audio for me. That's what its lot in life is. That's what the digital to analog converter does. It is very literal in its description. Take digital, convert it to analog. And on the last episode, I got everything wired up between my digital to analog converter and my Raspberry Pi. Let me turn this camera a little bit so that you can follow me a little bit. So I am going to get over here into the darkness, but I have hooked up 3 logic analyzer probes from my oscilloscope to my Raspberry Pi. I can get a little bit better view of that if I take my camera out. So I have a logic analyzer pod coming from the back of my oscilloscope. We call it an MSO, mixed signal oscilloscope. This gives me 16 digital lines. I'm using 3 of them. One to look at the clock for I2S, one to look at the left-right clock for I2S, and one to look at the data. And let me hit start so that we know I keep on time. Now, since I have that hooked up to the oscilloscope, I should be able to see that on the screen when it goes. I also have hooked up a regular old scope probe. So here's my regular old scope probe. I'm looking at the analog output from my from my digital analog converter chip, because I'm just curious to see if I get sound. I also have a new speaker here. So eventually when I get sound going, I'm going to use this speaker that replaced my lovely orange speaker. Rest in peace, lovely orange speaker. I really miss you. But this speaker is going to make sound go into our ear holes today while we experiment with how this digital analog converter chip works. We also need to discuss a little bit my decision process for the distribution, the Raspberry Pi operating system that I chose to use. So I had 3 choices. We'll get into why I chose the one that I did, and we'll get into how that works. But before I do that, I just want to make sure that I have everything connected. So I'm going to turn on the oscilloscope, get the Raspberry Pi powered up. So I'm actually using just USB to power the Raspberry Pi. The Raspberry Pi is designed to work with the USB power supply, 5 volts, which is what USB 2.0 does. And I'm going to send some sound from my phone to the Raspberry Pi, and I'm going to see if I pick that up on the oscilloscope. And you know what? Before I do that, the first thing I need to do when I sit down in front of the oscilloscope, preset. So let's preset. We're preset. Now on my phone, I have an app called the Tone Generator. So this guy is going to generate tones just like we were doing before with the Bodhi plot. If you remember, we were making tones with my Bodhi plot. And I need to send this. One of the things I'm really excited about is the ability for the Raspberry Pi to act as an AirPlay receiver. I have an iPhone. AirPlay is how I can send audio or video wirelessly from my iPhone to the Raspberry Pi. So that I'm using an AirPlay receiver here, and I'm attempting to send 100 hertz tone. So let's see if I'm actually sending 100 hertz tone. So I can see the audio signal here has cranked up, which is a very good sign. I'm at 100 picoseconds, or I'm at 10 nanoseconds per division, which is way too slow to see 100 hertz. So let's make this way bigger. Way bigger. Oh, there we go. Now we're seeing it. There we go. You can see it in the background. There we go. I should probably scale it so it fits on the screen because I don't want to clip. There we go. Perfect. Looks great. Let's do a measurement. Let's see if it's 100 hertz. So I can turn on my measurements here. Go over to frequency, channel 1. What are we looking like? That looks like 100 hertz. All right, let's move my trigger level up a little bit so we don't bounce around. Are we going to bounce around a little bit more? Of course we are. If I turn on a digital filter here, let's turn this on. There we go. So remember, I'm very interested in frequency components that fit into my ear holes. The oscilloscope that I'm using today is an RTO 2044, which, if I go back to my setup here, 2044, can we focus on it? There we go. 2044, you can see right there, is 4 gigahertz. Does anybody remember what our hearing range is limited to? Anybody? Is anybody there? Is anybody around? I can't remember off the top of my head. I think I can. I think I can remember. Let's see what the chat says. Yes, there we go. We have a great answer. Thank you. Sushma, great. It is 20 hertz to 20 kilohertz. That is what your ear holes can hear. So I am going to filter off the frequencies that I don't really care about. So I have a great mode in here called high definition mode. I'm going to limit to 1 megahertz. Actually, I could limit it down to 100 kilohertz. I can't hear anything up to 100 kilohertz. And as I have proven over and over again, my ears kind of run out of gas at around 16 kilohertz, probably because I wrecked them listening to really loud music. So now I have that low pass filter on, only allowing frequencies into the front of the oscilloscope that I'm interested in. And now you can see the signal looks super clean, super clean. There was a question on where did I get this app? This app that I'm using today is called ToneGen. You can get it on the App Store. If you just go to the App Store and look up ToneGen, you can do it, and then you can send tones out to your amplifier to see what it sounds like. So this is my 100 hertz tone, which looks great. It is 100 hertz. But that is the analog representation of the tone, and I am kind of interested in the digital representation of the tone. So I need to go to... Wait a second, I can never remember where to turn it on. Don't tell anybody, but I always turn it on from the front panel. It's funny how you get locked into use cases. So I'm going to turn it on from the front panel. I enabled the digital lines. So these are my digital lines. So these lines down here, D0, D1, and D2, which I will label so that we can figure out what is what, represent this analog waveform. So I can actually divide this up into 2 grids, make it a little bit easier to understand. So down here on the bottom in this grid, I have all my digital lines. Up here at the top, I have the analog. So this is the digital side, and then the digital to analog converter is taking these digital signals and converting them to this analog signal. It is working spectacularly. If I do a single, and let's zoom in a little bit. So I can take this right here. Let's zoom in a little bit. Now I can start seeing what looks like digital signals. Move this in. Move this side in. Hey, that looks like 1s and 0s, all right, guys? Are you not entertained? Okay, so I think we can make some labels now because I can tell that D0 is my clock, D1 is data, and D2 you can see is left-right clock, which is kind of neat, right? So that tells me how many bits are in each, well, in this case, a 32-bit word. It's a 32-bit word that is coming in, and we can actually count that and figure out exactly how this whole system is working. So let me add some labels really quickly. This will be clock. This will be D1 is data. Did I forget to hit enter? I did. Clock, data. And then this will be left-right clock. There we go. So now we have some labels. This is a pro tip for when you later on you make screenshots. If you're trying to make some more detailed measurements, it's really handy to have some labels on the screen so you can figure out exactly what the picture represents. If you don't have labels on the screen, you will swiftly forget how things were connected. D there was a reference, I missed it. D2 is the Mighty Ducks 2. I remember that when I was a little kid. The Mighty Ducks were a big deal. I loved that movie. That was a great movie. Okay, so let's learn a little bit about our bus. This is our bus. Let's go back to my desktop, look at the data sheet. So the DAC I'm using is a 32-bit, 384 kilohertz PCM interface. So it will take in 32-bit, up to 32-bit words representing the audio data, and it will output an analog waveform with a bandwidth of up to 384 kilohertz. So this actually clues me in on a little bit of my scope setup that I need to change. I need to change my scope setup from 100 kilohertz. Let's change it to 400 kilohertz. That way, is it 500? Will it not do 400? There we go. Let's change it to 500 kilohertz because that's what my scope will do. So I'm going to change it to 500 kilohertz so that it matches what I am measuring. You do want, another tip is you want to make sure that your measurement system matches the thing that you are measuring. That is why we are not measuring this 384 kilohertz device with 4 gigahertz. That doesn't match. But 500 kilohertz does match 384 kilohertz. We are in the same ballpark and everything is looking good. Okay, so it's 3 wires, which we set up. It's clock, left, right clock, and data. And it can go 16, 24, or 32-bit. So I'm curious, what is my bus now? Like, am I using 16, 24, or 32 bits? If I go back to my oscilloscope, we can count exactly what's happening. Okay, if I'm adjusting the zoom a little bit. Adjusting the zoom so that we can count how many bits. So here we go. This left-right clock, this 0 on this left-right clock right here represents 1 word. So how many bits? And I can count the number of clocks. So if I turn on some cursors, let's follow D0. Where did my cursors go? Guys, get on the screen. I'm dragging the wrong thing. I want to be dragging the cursors. Oh, guys. Okay, there we go. Get that into my zoom window. Get that into my zoom window. We got some in my zoom window. Here we go. Okay, so let's count how many 1s and 0s there are. So we're going to follow the rising edge. Everything's going to happen in this bus on the rising edge of the clock. So there is 1 clock, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wrist is getting tired. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. 32 rising edges on the clock while this left-right clock is low. What does that tell me? What do I learn from that? That tells me that this bus is using 32-bit words, which is great because that was the maximal amount of bits that I could use. And more bits actually allows me to have more voltage levels. So if I have more bits, I can have more voltage levels on my analog waveform. And that gives me a purer tone, a purer representation of the analog waveform digitally. So, what do we think? Are we happy with that? We got digital waveforms down here. We have analog waveforms up here. Another thing that I want to test is hook up this speaker that I have. So I have a speaker right here, and I want to hook it up. Let's see, here's my speaker. I want to hook this speaker up to the analog output of that digital analog converter chip, and just make sure that it is making sound and I'm not misinterpreting anything. Okay, so we turned on. Oh. I can hear the 100 hertz tone, but it's not plugged in. It's just getting it from as a Bluetooth speaker from my phone, so that's a little bit of a cheat. Let's plug in the cable so you can see I have my audio cable right here. Let's see if I can insert it. And can I disable Bluetooth? All right. I think I got it here. Go back to my tone generator, make sure I'm playing the tone. Make sure it is going to the Bluetooth, to the AirPlay receiver. There we go. There we go. We can hear the tone, so that tone is loud. Let's turn it down. That is a loud tone. That's good. That is good. That means my DAC is actually working. So my digital analog converter chip is working great. This is great news. This is also means that, remember when we tuned our amplifier earlier to make sure that we weren't overdriving the amplifier chip. So here's my amplifier chip. Let me put it on top here. This is the guy that we were using before to make sound. And we tuned these potentiometers down here at the bottom to make sure that it didn't overdrive the speakers. And I need to redo that now that I'm using the actual DAC, because the DAC, if I look at the DAC, it has different analog levels than, I think we're actually just fine. It has different analog levels, so a different amplitude than my iPhone audio output. So I need to account for these levels. This goes from 1.2 volts from plus 1.2 volts to minus 1.2 volts. And I don't think the iPhone had quite that large of a swing. This would have been a great time for me to have written some numbers down from previous episodes. But you know what? I can write it down right now. So I know that my DAC is going from 1.2 volts to minus 1.2 volts. One thing that I can do here is I can save a screenshot. So let's go in here and we'll save as. Let's call it something useful. So we'll call it DAC output voltage. Now, when I go back to measure my iPhone output voltage, I can have a comparison. So 1.2 volts to minus 1.2 volts. The next thing that I wanted to talk about really quickly while I was here is why did I choose this particular Raspberry Pi distribution that I'm using here? So which one did I choose? Why did I choose it? Let's go over the choices that I had at my disposal. So if I go back to my desktop, let's look at my web page here. I have three choices. I had this one, which is the Mood audio player. I can load that onto my Raspberry Pi. I could use Max to Play, it's an operating system. They wanted to be very clear. Max to Play is an operating system. And Volumio. So Volumio is actually, of the three that I had to choose from, was the only one that I'd ever used before. And if you go over here, one thing that was a little bit surprising for Volumio is that when I first started, it was totally free, and then it started to cost money. And if you've ever messed around with any kind of Raspberry Pi operating system, sometimes they're worth money, sometimes they're not. What really gave me pause is per year. I hate the per year idea for an operating system. Max to Play has a not a per year, you just buy it. But I wasn't sure which features I needed, because the different, I guess the different levels offered different features. So you could buy different packages to add into this Max for Play. It does have a lot of packages. One of the packages was AirPlay. One of the packages was Bluetooth. This guy, I think, let's see, this one adds Bluetooth audio playback. So all of them have AirPlay by default, but I think Volumio adds Bluetooth audio playback on the $28.99 per year, and Max to Play, you have to buy the AirPlay or the Bluetooth as well, which was kind of a bummer. But Mood Audio offered it all free, so you could go to the feature set, and you had Bluetooth audio and AirPlay all in one. And the other thing that it did was it logs in automatically to Spotify, so it becomes a Spotify receiver. So I am currently running Mood Audio, and we can actually check that out. Let's see, make sure I'm not missing anything in the chat, like anything crazy. I am not missing anything in the chat. If we go to mood.local, we can actually see the Raspberry Pi on the network. So AirPlay is active. Let's disconnect AirPlay right now. Hopefully. So we disconnected AirPlay. Actually, if you go over to the scope, you can see that I've disconnected AirPlay. So the analog audio is gone. The digital audio is quiet, which is a great sign. It means that the DAC is working perfect. Oh my gosh. Oh, what do we got? 5 minutes remaining! 5 minutes left. We have 5 minutes left. We have gone super long. I apologize because my mic wasn't working at the beginning. I was getting too cavalier with that microphone. Okay, we're back though. So we're checking out this audio source, the Mood audio player. If I go to settings, which is where I'm gonna be most interested. I mean, I could stream something. So if I get my scope up here, so I can get my scope on the screen, you should be able to see the scope and my Mood audio player at the same time. If I hit play right here, go back to the scope, you can see, boom, I got digital audio. This is the analog audio, so it's working great. My digital to analog converter chip is working spectacularly. But I'm going to pause that. If we go back to the scope, you can see that the activity is down, so the digital bus is off. I mean, I love the scope is actually able to tell you all the details about your system all in one spot, both the digital, the analog. We've looked at the power, everything. It's one of the reasons why I love oscilloscopes. If I go to audio, so here's my configuration. I can go to audio, and one thing that you had to do is define the I2S audio bus. Now, this is something that I was curious about, so I'm using a generic one. Where was it? Generic, there we go. Generic Raspberry Pi DAC. So there's nothing special about it. You can also have a hi-fi berry DAC, which I actually have the hi-fi berry amplifier. So this is the setting that I use for that. If you change between these two, it doesn't actually change the digital traffic going to the Raspberry Pi. It remains 32-bit, which is the best. If it was 24 or 16-bit traffic, I would want 32-bit. Why would you not want more bits? If I could have more bits, you always want more bits. And there are no options over here. Another thing that you can add is a USB volume knob. I don't know if anybody would be interested in me adding that to this setup. I can turn on the Bluetooth adapter. I haven't tried that. I do want to try that because the Raspberry Pi does have a Bluetooth radio on it, so it should be able to just automatically receive Bluetooth signals, which occasionally is useful when I have an app on my iPhone that does not support AirPlay. I'm going to fall back to Bluetooth. There's a couple of games that I play that don't have AirPlay, but they do have Bluetooth. And then Spotify integration, so I definitely wanted that to be able to have the Raspberry Pi communicate to the Spotify server independently so that my device is kind of out of the way, and now it's just between the server and the Raspberry Pi. So that's what I'm doing. If there's interest in checking out the other distributions, I would be happy to do that. I mean, I think it'd be really cool. It would be worthwhile And kind of an interesting science experiment, since we're just really experimenting, I could check out what does max to play look like. We could look at that on an episode, and we could check out Volumio, which I actually really like. We could check that out on an episode. There's a question: what is a USB volume knob? It's a volume knob that outputs in USB. I suppose we could probably, let's see if we can find one really quickly. Before I'm not going to show you the Googling, because I'm going to be honest, I get a little nervous about Googling live on camera. I don't know what's going to happen. Here is an example of a USB volume knob, though. If I go back over here. Here we go. Here's one. So I think this is what they're catering to, something like that. So it's really just a potentiometer hooked up to some kind of USB chip. So there's actually going to be a chip inside of there which will digitize the potentiometer and spit out USB traffic representing the level of this potentiometer. Another thing that you could do is actually use a rotary encoder. So I could hook a rotary encoder up to a pin on the Raspberry Pi, and it could be a volume knob, which is a totally neat option. I don't know. We could have like a volume knob that has some LEDs that kind of represent the level, and I could go up and down, and a digital volume knob, which would be really neat. I don't know if that's the direction we want to take it. I'll tell you what, though. I'll leave that to the comments. And this is it. This is it for the day. It's been a great Baby Friday. I'm going to put my bedazzled hat back on to celebrate Baby Friday. Remember, resistance is not futile, but it is voltage divided by current. And it also isn't futile. I don't know all the nerds in the world, but I would love to meet them. So please share this with a nerd in your life. I'm going to hang out in the chat for a little while, just chat with you guys. And, oh, let's throw my autofocus off. My autofocus is getting super confused. If you want to connect with me, you can also hit me up on Twitter and Instagram at OscopeWizard, and I would be happy to hear what you think. Let me know in the comments, should I add a USB volume knob? Should I add a rotary encoder? Should we do the other different distributions? Or do we just want to get to the point where I'm hooking the amplifier up and making noise happen into our ear holes, which I'm very excited about. And of course, at some point, I need to build a box, which is not my strong suit. So if anybody has any suggestions over box building, about box building, let me know in the comments as well. As always, thanks for watching. See you next time. Bye.